Hello, so this is the first video in a series of videos I made on machine learning core concepts. I'm going to start with the absolute basics, and that is simple linear regression. So today I'm first going to go through a little preamble because this is the first video in the series. I'm going to explain why I'm making these videos, why I think they're important, at least for me. I'm going to talk about simple linear regression and my philosophy, for lack of a better term, around it. And then we're going to go through some from scratch Python code using Jupyter. From scratch is in quotation. I'll let you know why that is when we get to it. So we live in a golden age of language models and machine learning packages, Python. You're able to capture so much with just a simple line of code, which 20 years ago would have been thought to have been impossible. This image on the left, I'm just using Google, and I said write Python code using scikit-learn random forest, and on the right here it gave me all of these libraries, and I didn't include it here, but it gave me all the necessary code, gave me the data set, scalar, accuracy metrics, the model, train test split, all of that spelled out underneath. And so there's a sort of trend in data science where machine learning is becoming more like prompt engineering, where you can just use LLMs and use existing packages, and you can basically do any kind of robust model that you can think about and apply it to any data set by just using, not even being able to code, just using simple prompt engineering or just input prompts with LLMs. So I think that's really powerful. I use that all the time. That's the way things are going. There's no fighting it. But I would caution people who are new to data science or new to machine learning that this shouldn't come at the cost of knowing what's going on underneath, being able to make these yourself, being able to pick them apart. You know, the analogy that I would use is the difference between being able to drive a car and being able to build and repair a car. Because when things go wrong, which they will, the LLMs won't be able to help you. You're going to have to have a very intimate knowledge of what's going on. Just like when your car breaks down and there's no one around to fix it, if you know how to build and maintain a car, you're going to be able to fix it yourself. Same with these algorithms. So I understand this is a bit like the old man yells at cloud meme, and I recognize that. I'm not saying that you shouldn't take advantage of these tools, because again, that's just the way the industry's heading. But I do think that you should understand at least the core algorithms and try to do them from scratch. And what I mean from scratch is not without using any Python libraries or R libraries, but without using any of the machine learning libraries, so like scikit-learn. So try to see if you can build some of these yourself using just like NumPy, pandas, even just straight up Python. Alright, so simple linear regression. This is something that we've all heard about. It's simple. It's inherently one of the first things you learn in statistics, and people don't even really consider it machine learning because it's so basic, but it is at the core of machine learning. You have a data set like this. This is just some arbitrary data set. You have a y variable and an x variable. You plot them, and then you might put this in Excel or Python or Tableau, whatever, and then you can generate a line. Say add trend line, okay, and then that's it. But the question is how did the software find that trend line? I think if you understand that, you're going to understand how all of these more complex downstream algorithms work. What makes this line best fit? are we just drawing a bunch of lines and eyeballing them and saying like, oh, I think this one fits the best? It seems to be in the middle of everything. Is there some guiding mathematical principle? What is that principle? Do you know that there's some mathematical principle, but I don't really know what it is? So if I gave you this data set, which is just 4 entries, all integers, there's just 2 variables, x and y. Do you think you could calculate the line best fit using these? Or maybe there's some equation out there that can do it, but I don't know it. It doesn't really matter. I think that this is one of those things that you should have in your mind, like exactly how this line is calculated using data, why it's calculated, what drives it, what are the derivations behind it. You don't need to be able to derive it yourself, but just to know that they're there, that there is some sort of reasoning. And I think if you understand that, you're going to know the guiding principles for almost every predictive and honestly unsupervised machine learning model. In this case, in simple linear regression, we have 2 variables and we're trying to find the line best fit. Well, with neural networks, we're not looking at a line best fit. We're looking at like a squiggle or some sort of noisy signal best fit. It's much more complicated. It's not straight linear like before, but it's the same kind of principle. There's the same things guiding this. Why this squiggle as opposed to any other squiggle? For something like principal component analysis, which is a dimensionality reduction algorithm, it's why are we projecting onto these principal components versus other principal components? What are we trying to maximize? What are the guiding mathematical principles between that? I think if you know simple linear regression, all these other algorithms actually follow sort of the same logic. So you probably know about residuals. Residuals are just the difference between the predicted value, in our case of simple linear regression, that's a line, the difference between those predicted values and the actual values. So, and we typically square residuals to counteract any negatives so that they don't cancel each other out. You might be asking, why don't we use absolute value? That's a good question. I think there's a lot of debate on that, but also squaring them helps exaggerate differences between outliers. So outliers are going to contribute more to the overall residual sum of squared residuals more than data points that are closer to the predicted value. So again, you probably know this, but take this line for instance. Somehow the computer has plotted a line like this and it's showing these residuals. And you say, okay, well, we want to find the line that actually minimizes the residuals, the difference between the predicted value. But how did the computer find this line to begin with? Right? A line is, in a 2-dimensional sense, it's just the simple y equals mx plus b. Did it just pick random m's and b's and plot that and take a bunch of residuals from each one and sum them up and then see which one had the lowest? Is there something else that's guiding it? So I think if you can't answer that question, that this is a good video for you. So I want to talk to you about something called a loss function, and this is from the IBM website. So this is just a quote from IBM. In machine learning, a loss function is used to measure model performance by calculating the deviation of a model's predictions from the correct ground truth predictions. Predictions might be misleading for this second thing. It's actually more like just the actual data points, right? So right here, the red line represents our model, in this case a line, and all the predictions are going to be whatever x values we plug into our line equation. And then the difference is going to be between this actual value and our predicted value. Optimizing a model entails adjusting model parameters. So in this case, our model is a line, and the parameters are the coefficients or the slope and intercept to minimize the output of some loss function. Okay, what is our loss function in the case of simple linear regression? What are we going to use to guide us towards best fit? Now, different machine learning algorithms have different loss functions. In fact, even simple linear regression has different loss functions depending on who's calculating it. But the overwhelmingly popular loss function for simple linear regression is the mean squared error. So this is exactly what we were just talking about on this last slide, but in more formalized terms. So MSE, the mean squared error, is equal to 1 over n. N is the number of observations, and is all of that times the sum of every pair of y sub I, which is a data point, minus y hat sub I, which is, in our case, is what our model is predicting, squared. So you're going to take the difference, that's really the residual, between the real data point and the predicted data point given to you by the line. You're going to square that, and then you're going to add them all up, and then divide by the total amount of observations in your data set. So this equation will actually guide us to how we're going to figure out what our parameters are. Let's assume we don't know what the slope, the optimal slope, and the intercept are to yield the best, the line best fit. But we have this. This is what's going to guide us. So what is this term again? This is our predicted output. This is what the line predicts. Well, that's just going to be the y equals mx plus b, or just mx plus b, right? Y hat sub I is just going to be this mx plus b. We don't know what m and b is, but we can plug this into to the mean squared error, and do some math and figure out what those are going to be. Yeah, exactly. What are m and b? We don't know yet, right? We could theoretically just plug in a bunch of m slopes and intercepts, take the mean squared error, and see which one yields the smallest one. And that is kind of how some machine learning algorithms work, or how optimizing some machine learning algorithms. Because for simple linear regression, there is actually a very elegant solution, but for certain machine learning algorithms, there isn't. You do kind of have to just plug in stuff and see which one yields the smallest error or the smallest output in your loss function. All right, so it's time for code. Just going to